Okay. So I was looking at the homework. When is the homework? The homework seems to be due on Thursday, not on Tuesday. And why was that? Why was it not made due Tuesday? Do you guys remember that? Yeah, because I don't know. I think I probably intended to make it Tuesday, but then it was a mess. So what will? So it's I'll make the rest of the homework slowly. I'll adjust it a little ahead. Like the next one will be still on next Thursday, but the one after that will be on Tuesday.
Yeah.
Okay. So because I think I can cover things before. Just be aware of that. Doesn't matter. I'm reasonably flexible with this. So for now, we have homework 8. Which is still you should be able to finish this. Homework 9 will be I think I should be able to cover the concepts by Thursday, but make you put it. Final exam. This is readable?
Yeah.
Small. Light. Let's see. We talked about dynamics, like when charges are moving around. So we got away from statics. So we found the Green's function for understanding of describing systems when things are moving. And the primary idea is that it's very similar to the earlier scenario, but because of the constant speed of light, the maximum limit, everything is retarded. So whatever we see today has happened sometime in the past when we see the stars that, or when we see the stars, that's a picture of the universe sometime back, and that's what is called the retarded effect. And we want to see how we can make this better. But most of our equations will be harder to work with, but there is one limit in which it gets very nice and simple, and that is the scenario when the distances are very far away. It's called a far field approximation, and that is a significant, you can do a class of problems for that. And this is called electromagnetic radiation in general. So this is electromagnetic radiation. And one can, of course, do this more accurately, but we will mostly work with far field approximation. Far field limit. And I'll say what does it mean by far field in general. We have Maxwell's equation, and if we introduce potentials in the following form, electric field, so this is R and T, right? Everything is in time, not Fourier transforming anything, and it is negative gradient by electric potential, and time derivative, the vector potential. I will not write the explicit dependence in every step, but here the first step it's clear that this is position and time are dependent. The magnetic field is equal to curl of the vector potential. In terms of this, we could conjugate or mix up Maxwell's equation, and we showed that is electric potential satisfied square plus 1 by c square, that's wave equation, but with a source. Both the electric potential and the vector potential satisfy a very similar equation. Now, like if we were to have the T dependence out, that is statics, then basically that's electrostatics. Same thing for magnetic potential, very similar, except the source is now current. It's mu naught times J, or current. These equations assume a gauge, and the gauge is so the gauge we use is d mu times a mu is equal to 0. That's equivalent to, so that's del started with A, that's the divergence of A, and our time derivative, since it's downstairs, that's 1 d by dt, and there is also a phi over c, the zeroth component of phi has a c, so that's plus 1 over c square times d by dt phi is equal to 0. So that's a gauge we have chosen. Even when we are doing magnetism, we choose a gauge when, but again, we can read it out from here. In statics, this becomes 0. This is called the Lorentz gauge. Then that's called the Coulomb. Is this readable, or should I change the pen? Okay, so whenever we have a differential equation with a source on the right side, we look for, we construct a Green's function, and the Green's function we constructed was square plus 1 over c square. So at a particular time, instead of having any charge distribution, we say that it is very specific at position R and at time t. R prime. So the source is at R prime t prime, and that's your observation point for t, exactly like the electric potential to your point charge. The source exists. Sorry, what is it?
G minus t prime.
Yeah, that's one more. Right, what it means is that the source exists only at one point R prime and at only one time T prime. So at one instant that, and if we have one contribution at one time, then we can add up all the times. As far as we not violate causality, that's okay. Okay, so the Green's function we showed was equal to uh, 1 over 4 pi. So there's a, so the denominator is pretty much the same as a scalar piece, so it's r minus r prime. And if the denominator was the only thing there, so that's exactly the static case, as the numerator has this retardation feature in it, so that's t minus t prime minus r prime over c. It basically says that only those times that are connected to the source, observation time and the source time, only if they are connected by the retardation factor of the distance light takes to reach the observer, only when they are matched, only then this Green's function contributes. The delta function says that if it doesn't match, then it is zero. So that's the retardation condition if you want. So that's your background, and now we want to put this back in, right? So if we put very general, we don't want to specify what is rho and what is a, what is j. What we did in a previous example was that we specified rho and j. We said that a charge is moving in a straight line with uniform velocity. We specified this, and then we got the phi, and then got the electric and magnetic field. At this stage, what we want to do is that we want to keep this general. The idea would be that you want to be able to keep any source you want in a lab and do the observation possible. A simple possibility is that you want to design an antenna. Antenna will have J's in it. What kind of J will give you a certain kind of radiation? If you want a radiation only on one corner of the room, which is focused on one side, so what should be the properties of JB so that you achieve that? So that's sort of a motivation that you could have in mind when you're doing this problems. Okay, with that, let's proceed. If we know the Green's function, we can just substitute this. So basically invert it, right? Green's function basically inverts the problem. So if you have phi, or if you're interested in phi, this is the contribution from one point, integrate over all the sources and all the times, and you get your phi. So this will be equal to 1 over 4 pi. Let me write that in 2 steps. This is equal to 1 over epsilon naught, integrate over all sources, integrate over all times. All sources, this is all space you're integrating, and this delta function will make sure that it contributes only when the retardation feature is taken care of. And then you do Green's function, or comma t, or prime, comma t prime, and rho, or prime t prime. Again, think of this as a point charge, right? If this is the contribution from a point charge, and you multiply it with the charge density, you get the complete. It's a superposition principle. If you want one point charge is without the integral. If you want all the charges, you just integrate with the charge density, and you get the electric potential. Is that clear? So that should be fine. So now substitute this in here, and you immediately get the 4 pi in there. So that comes out. And this is d cube or prime t prime, and then the delta function t minus t prime minus r over this charge density of prime t prime. If you know rho prime, then an easy integral to work out is a position integral, but we want to keep this general. So the right way to proceed is to do the time integral. last time when we were given the charge density, we actually did this integral because they were delta functions. But now we'll proceed and do the delta function for time first, and immediately you see that this is doable. You just have to replace wherever you get t prime with t minus this quantity. That's equality, right? So that's equal to 1/4 pi epsilon naught. Now integrating over all positions, time integral is done. So this is charge density r prime minus t, replace the t prime wherever you see with r minus r prime over c. And you clearly see that if this was 0, if this was not significant, then that's the same old charge density divided by r. So it's just the retardation that's changing. So that's the only quantity, but also r prime goes in different places now, right? R prime is here and here. R prime has gone into the time. Time dependence has an r prime in it. So that's one feature. The vector potential pretty much satisfies the same thing, correct? It inverts itself, and if you replace phi with a and rho with j, you pretty much get the vector potential. So let's write down the vector potential. So a of r comma t is, instead of epsilon, now that is mu naught over 4 pi. Otherwise, mostly everything is the same. So if I were to rewrite retarded time as t minus r prime over c, it's clear that take your static situation and replace your time with the retarded time, and it seems like it gives you the radiation formula. But it should be noted that r prime enters here, and it's not straightforward. When you take the electric field, for example, when you take the gradient, now you have to hit the appropriate places, right? That will hit your r there, and accordingly you have to worry about those. So we'll see that in a minute, but before we start doing that, let's see the static scenario a little bit better. So what we typically have is a scenario where charge density and current density are confined in a region. And this could be a lab setup where you have a sample that is moving around in the center of your, let's say, the center of the room, and you have a detector somewhere here. Right? That's your R. Right? That's observer. That's your source, and this does something, and the radiation goes in there, and you're making the observation in here. So what you would like to say is that this is R prime, that's your R, and this is R minus R prime. Right? That's what the quantities that you see are. And what we are saying here is that if the time taken to go for light to go from here to there is significantly large, then you don't have to worry about this term. So let's consider the scenario that R minus R prime is significantly smaller compared to the the t itself doesn't make sense because it's an observation time. Instead, what you have to talk about is that there is some change happening. So there is usually a system, for example, if it's a wave, the time scale is that wave goes up and then down. Something has to repeat itself. That is a difference in time that you talk about. So there is a characteristic time that you can talk about. So C tau. This is a characteristic time, which depends on the specific system, right? Unless I tell you what the system is, that the characteristic time doesn't come in. Have in mind something oscillating if this was moving around. So it happens in a time, has a time period associated with it or a frequency associated with it. So this is a property of the system, right? The system is doing something in a certain amount of time, and that's what will decide what the observer will see. If this is extremely small, then you can neglect this piece altogether. Right? You can neglect this piece altogether, and that's what is called statics. Right? That's statics. We are interested in the opposite regime. We are interested in the situation where r minus r prime is very much greater than c times c over g tau. And this will be called the far field approximation. Or maybe I should not say this is the far field. Let's say this is, like, if that is true, then you cannot neglect these things. And let's say this is radiation in general. But to achieve this, I can say I will just talk about the situation where r is very much greater than r prime. R is very much greater than r prime. Like in some frame, you keep your origin somewhere here, there is an r prime, and r is significantly larger, then this will be far field approximation. Okay. That's what we want to see. And so what are the consequences? We will see that in just using this approximation, these integrals will become much significantly simpler. So let's see what is the approximation. Any questions at this stage? Okay, so let's investigate what is r minus r prime. And it is a magnitude that comes into this formula, right? That is r minus r prime here, r minus r prime here. That's the two quantities that comes in. This is the same as square of this quantity. So this is r minus r prime square. That's a simple definition if you want. This is r square plus r prime square minus 2 r dotted with r prime.
Can you change the
Pen. Oh, change that. Okay, yeah. Pen, right?
Yeah.
Yeah, let me change pen. Okay. Yeah. Better?
Yeah,
Much better. Okay, so that's r minus r prime. Okay. Okay, so that's what it is. This is exact for now. Let me pull out an r, and this becomes 1. This term I write first. So this is 2 times vector r over the magnitude of r dotted with an r square I'm dividing, right? So this is r prime divided by magnitude of r, and that's plus r prime over r square. Notice that this is second order in R. So there are 2 R prime over R's. So this is R prime over R square. Here there is only R prime over R. This is a R hat. This is the same as R times R hat, right? This is of unit magnitude. That's R hat dotted by R prime over R plus order R prime over R square. Is that clear? This is leading order, or this is 0th order, first order, second order in R prime over R, which is the condition for far field approximation. Right? In the far field approximation, this doesn't contribute. This is significantly smaller than this. In that same approximation, I can also expand the whole binomial expansion for square root, and I get R times 1 minus 1 by 2. That's a power of this binomial, 1 by 2, and then 2 times R hat vector R prime over R, and there are higher orders if you want. Okay.
We expanded the polynomial.
Tell it again.
We extended the polynomial. And
Correct. Expanded this square root radical in there. So 1 minus x square root is 1 minus 1 by 2x and so on, right? So it is next term will be plus 1 by 2 factorial of 1 by 2 times 1 by 2 minus 1, n into n minus 1, right? N is 1 by 2, and then minus x the whole square and so on. Right.
Yes.
So I'm interested only in the leading power and dropping everything. That's as far as I consistently drop it, that's okay. So that's what you get for this. So what we have here is the condition becomes R minus R prime. Magnitude is expand this out R. 2 cancels out, R also cancels out. So this is unit vector. The is almost if R prime is small and R hat is pretty much the direction between the source and the observer, but it could be off, right? So you have to be careful. Dotted with vector source prime. Like it's like saying that you have some source points here. That's your observation point if you keep your origin there. So that's your R. And R prime is notice our direction between R prime and R is playing a role. It is not exactly between the line connecting them. This angle matters. So that's one piece. And yeah. Okay, so if we use that feature, we can put this back in here. So basically, this is in the denominator. So notice, let me also do, before I go there, let me say that 1 over R minus R prime is equal to 1 over, let me go here. So I have 1 over R, and in the denominator, I have 1 minus R hat dotted with R prime over R. Right? plus higher orders if you will. But I again expand this out. So that's 1 over R. And expand out 1 over 1 minus X. And you get 1 plus R hat dotted with R prime over R. And what we will see is that this is not the leading order. I mean, already 1 over R captures is significant, whatever we are needing. This is the next leading order. So this we don't need. This is a higher order. One way to see this is that there is already a 1 over R, and R prime is there inside this source. So that's the second order, R prime over R times R prime over R. That's higher order. So we need to drop that. That's for consistency. Since we have dropped this R prime over R, so we have to drop that also. So basically the denominator has become very simple. So it's just 1 over R, the leading approximation. In fact, it is so simple that R does not even depend on R prime. So this can come out of the integral. Right? So it is significantly simple. So we just have to integrate over the current density or the charge density, and we are good for our radiation problems. So that is a simplification, and that leads to phi r comma t. Yeah, is equal to 1 over 4 pi epsilon naught. Move it out. It's 1 over 4 pi epsilon naught r times 1 over r. That's pretending that whatever is the source is all static and right at the center here over the diagram, right at the origin here. Then that's the contribution from that. And the charge, what is the charge? Effective charge is basically d cube r prime rho r prime minus, that should be a time, but this is retarded, and t minus vector r hat dotted with r prime. That's a simplification we have. But notice now, so there is a position dependence in here, and we should be careful about that. Yeah. Make sure. Yeah, that's a mistake, right? Yeah, what's a mistake? So I was supposed to replace this, correct? So I replaced only this and forgot the R, and yeah. So it is T minus R over C. So I'm replacing this in here or here. So it is R over C plus R hat dotted with R prime over C. That's my retarded time. So it is one is the time that it takes to go from the source point all the way till here. But then you have to accommodate for this point also. So even that tiny length difference is contribution. But the nice feature is that the denominator could be goes away, and that's a significant simplification. The vector potential similarly is relatively easier. It is mu naught over 4 pi, that is 1 over r, and again, same idea, dq.
It should be J.
Oh, that's big change. Good, thank you. And one would think that, yeah, I've just replaced it with time, but the point is that when I'm integrating this, time contribution actually contribute to the r prime integral. So the new functional dependence in the fourth coordinate, which is time coordinate. And then, okay, that's pretty much your expression for your scalar potential and vector potential. But we would like to proceed and get the electric field and magnetic field, right? Electric field and magnetic field are given by these expressions. So we have to take the gradient of phi, time derivative of A, and if we know the gradient, then the curl is also reasonably easy to do. So let's see what happens when you're taking the gradient of phi. So phi has r dependence and t dependence. Of course, when we say there is a gradient, what it means is that you're hitting anywhere that is an R. And where are the places where R is? So you go in, there is an R here. That's one place there is an R. The next place there is an R is down here. Right? It's the magnitude of R. And third is this is an R hat, which is an R. Right? So there are three places where there is an R, and we have to hit each one of them. So before we actually hit it, so we have to work on this. Let's ask what is gradient of R itself, right? So let's prepare ourselves. So what is gradient of R? Right? Eventually I'll hit here and write everything. So that's gradient of R and 1 over R. And that's equal to, what is gradient of 1 over R? So this is minus 1 over R squared. This is like a chain rule, right? And then I have to hit the R itself. I have to hit the gradient of magnitude of vector R. Right? And what is the gradient of magnitude of R? That again? Yeah. Unit vector R, very good, right? So this is a good thing to remember, that this is R hat. Another thing good, that is only two things typically you have to do, you need for doing the vector algebra in E&M is that one is the gradient of the magnitude of R is R hat, and the gradient of the vector R is actually a diagonal. With these two, you can usually manipulate, do the vector algebra in E&M reasonably easily. So this is minus R hat over R squared. That's what we have. Another thing we will need to do is we will have to hit here, right? We will have to hit the gradient out there. So let's see what happens out there. So even before we hit it, so this is gradient of R hat dotted with R prime over C. Or actually, let's do this. Let me do this in the. I'm jumping ahead, I guess, just to collect things together. So let me actually physically do this. I'm going to hit here, and I'm going to hit this. So for that purpose, it is good to write this as, so this is gradient 1 over 4 pi epsilon naught. There's 1 over r, and I have dq r prime and rho r prime. And let me write this whole function as the retarded time tr. So that's just so that it is clearer what I mean when I'm making the differentiation. So it's t minus r over c plus r hat r prime. That's my definition. And that way of saying, I can either hit this or I can hit here. So I have two terms. One is 1 over 4 pi epsilon naught times gradient of 1 over r. But this remains the same. Don't touch my charge density. But the next one is I can hit here. So it is plus 1 over 4 pi epsilon naught, 1 over r, and this is a gradient in r. The integral is in r prime. It can actually enter the integral. It's dq r prime, gradient of rho. Okay. We already, or let's, let me write one more step. Or I can use the fact that this is 1 over 4 pi epsilon naught times this is r hat over r square. Right? That's what we did just a minute ago, including the minus sign, and dq r prime rho of r prime evaluated at the retarded time. And the next piece is what to emphasize, 1 over r dq r prime. I have to take the gradient of a function which has r inside of this t of r. So you use chain rule, right? So you first take the derivative with respect to this d by dt here, and then take the gradient of that. So how would you do that? So let me write this gradient as d by dr. So this is d by dr, right? Let me introduce a chain rule. So to do this, you would do dr over r, and that's d by dtr of rho of r prime. Is that clear? That's a chain rule, right? First differentiate it with t, the retarded time, and then take the derivative of with respect to. So this is like saying that if you have a function of x and then as a function of time, then derivative of with respect to time of f would be equal. First, you take the derivative with respect to x, and then you take the derivative of x with respect to t. That's a chain rule, right? Take with respect to x and x with respect to t. So take the derivative with retarded time and then the retarded time with respect to r. That's so the question comes: what is the gradient of the retarded time? So d r with respect to r, which is nothing but the gradient of t of r. And that's equal to a gradient of t minus r over c plus r hat dotted with r prime over c. This is going to hit only r's, so it will hit this r and this r hat. That's the only two quantities it will hit. T it doesn't hit, so that goes away. So that's the same as minus 1 over c times gradient of the magnitude of r, which we know is r hat. Plus, I have to go and hit this, so it is plus gradient of r hat is better written as vector r over r, because I know how to operate on vector r and I know how to operate on magnitude of r, so I write it like that. And that's what I want to evaluate. And then dot it with r prime over c. But this is going to hit both the numerator and the denominator. And remember that this is equal to 1 and magnitude it gives you simply r hat. Clear? Hit this numerator, this is r hat to begin with, so that's r hat over c. That has the dimensions of 1 over speed, that's distance over time, that's dimensionally okay. So this gives you plus. When I hit the numerator, I simply get a 1. Leave the denominator alone, dotted with r hat, vector r hat over c. 1 will make vector r hat the same. And next is minus 1 over r square. Over r square, gradient of r, which is r hat. And we still have vector r dotted with r prime over c. Cancel away one of the r's with this. That is a r in here. So let me write this as minus r hat over c plus 1 over c times, this is in the numerator, you have r prime, and this is r in the denominator. Use one of the r's to cancel that. So it is minus r hat dotted with r prime. That should be a familiar construction. And if you recall, if I were to do r hat crossed with r hat crossed with r prime, right? A cross B cross C, you get this is equal to vector r hat times dotted with vector r dotted with r prime. That's a center one, and the second one is minus r prime, because r dotted with our unit vector is 1. So that's equal then to minus r hat over c minus of r hat crossed with r hat crossed with r prime over r and 1 over c. All that has to go into in here. Let me check this. Something. Yeah, that's correct. Any questions here? So I'm just collecting terms here, and I was in the process of doing gradient of phi. I took a break there to evaluate this piece if we have 2 terms here. So there is 1 term from here, and there are 2 terms from there. Yeah. Okay. So what is my expression for scalar potential? It is this piece in here. That's the first piece. So I can write it as it is. 4 pi epsilon naught vector r hat over r square. And pretty much average of the charge density, but all evaluated at retarded time. Next piece, I have to put this in here. So there is a minus r hat over c. So this goes in here. And when it is r hat, I can bring it out. Right? R hat does not depend on this integral. I can bring it out. Let me do this slowly, maybe. So, this is plus 1 over 4 pi epsilon naught. Slowly, so this is 1 over r e cubed r prime, and substitute this. So this is minus r hat over c minus r hat crossed with r hat crossed with r prime over r over c. Both are unit vectors, or r prime is magnitude wise, that's right. But angular, it might contribute some angular feature. So times derivative, right? So derivative d by dt r of rho of so this has a full feature in it. dr, remember, is t minus r over c. That's the same as 1 over 4 pi epsilon naught r hat over r square q prime rho of prime here. That's the first piece. Second piece, bring it out, minus 1 over 4 pi epsilon naught. And this is r hat over r. And that is 1 over c there. So this is d cubed prime and 1 over c. Now let me write write this d by dtr as it is the time derivative of rho of r prime and t, but then I have to evaluate this at t equal to t of r, which is t minus r over c plus r hat dotted with r prime over c. Just a different way of writing this, making this more explicit that, okay, that's where the time dependent quantities are. So the change in charge density contributes to your, oh, this was gradient of a scalar potential, right? This was gradient. Okay. And that is a third piece, which is minus of 1 over 4 pi epsilon naught. And pretty much include r prime over r in front of this. So it's kind of the first moment if you want. So this is r hat crossed with r hat crossed with the next r is I can put this in here, like, and this is the cube of prime, and that is vector r prime. Right, this time I did not expand this, I just wrote it as it is. Like here, there's an explicit form, but these two are the same. This also should be written in this form if you want to, but this can be written in this form either way. So this was just to really emphasize that that's the form in which it is. Okay. Oh, this is an r square, right? That is already in r in here. So there's an r there and there's an r here. So it's an r square. That's crucial because if you were to think of this whole thing as a charge density, so that's an average charge density. This is a 1 over r square effect. We're talking about a very far distance. This is a 1 over r square effect. This is a 1 over r dependence, right? We're very far away. This will dominate this. And this is also 1 over r square. So overall, this is the leading order. This is higher order. And that's higher order. We are interested in the leading order. We are saying that something is happening in your lab and you're measuring very far away, but that measurement is pretty much infinity. Like it's very, very far away. It is like we looking at the sky, even though stars are not at the same distance. For our purposes, this is on a dome. For our purposes, there is a dome surrounding our universe, and all the stars are stuck on the dome. They are all at infinity. The distance between them really doesn't matter. So it's all on a dome. And in that approximation, that's a far field approximation. It's just this, right? So the gradient of phi then is r comma t is equal to just this quantity here. So minus negative gradient will be positive of that. Right? So it's 1 over 4 pi epsilon naught times r hat over r and the cube prime, and this is d by dt, charge density, and evaluate is at t equal to t of r, evaluate it at the retarded time. The higher orders, but we don't draw that. This is the dominant of on the dome. The leading order will be, and in that limit, extreme limit of r tends to infinity, which is exactly on the dome. So
There is 1 by C.
oh yes, 1 over c. That's 1 over c. Yeah, thank you very much. Yes, Krishna.
Yeah, I'm kind of confused on how we go from like del tr to del t and t evaluated it.
This one and this
Yeah.
one, this one
Like-
and where is that?
Pretty much that in the previous step. Yeah.
This and where is the yeah, here, right?
Right.
This one. Yeah, so it's a innocent definition, but has an emphasis there. Let's say that I'm talking about f of let's say derivative of yeah, so derivative of y is what we are interested in. Okay. But this is the same as derivative of with respect to x, f of x, and setting x equal to y. That should be the same. But now notice, what if I am taking the derivative of this could be half x squared, right? So this could be derivative of x squared and f of x squared. That's the same because it's just the same variable, but that can be thought of as d by dy of f of y, but then I evaluate y is equal to x squared. It's a way of writing, it's more of a notation, but to emphasize but I wanted to write it like that to clarify that this is not just the normal time. After taking the derivative, I have to replace all the times with the retarded time. So there is an r prime dependence in there, which will play an important role of that in the whole of radiation. There is an r prime sitting in here, and there is an observation point also sitting. So there is an observation point, and the observation point is here, here, and source point is in the r prime. So it's not that we have got, it's not that we are done with the integral. When we do the integral, we have to worry about that. So it depends on the source here, and it depends on the time also. So there are two places it depends on, in a sense. So clear? Helps. Okay. Okay. Yeah, I wanted to check this before I proceed. Okay. The curl will come out pretty much the same. Right? The curl will go through exactly the same steps, except this will become an A and this will become a J. Right? There is a curl cross product between them. There will be a cross product between them. Two vectors that will be cross product. So curl of A goes through very similarly. It's a, there's no negative sign, so I have to provide that negative sign. Provide the cross and that, and this is E cube prime 1 over C times the time derivative . Okay, so I know curl now, I know the gradient, and notice if I need the electric field, I need this piece, and I need the time derivative also. Okay, so where does the time derivative show up. It's just one place, I suppose, right?
R by C.
R by C, this t, right?
Oh, yes.
That's the only time derivative, correct? This doesn't have any time derivative, and it's just this point. So let's collect that, and what can I do? What can I erase? So I have 5, so I can erase this part, right? We took care of this. Maybe I will need this, so in case I need it. So almost there, right? Once I have the time derivative, then I just start collect things together. Okay, so derivative of A with respect to time, it seems like that's just one piece in there, and I want to write it in the same format as this. So I do mu naught over 4 pi times 1 over r d cube r prime, and I do the same idea that this is d by dtr and d by dtr over dt. I think so. And j of r prime here. Okay. And derivative of tr with respect to t is of course 1. Right. So this is of course 1. Oh, I remove this. I want to write it as much as possible as that. So what I do is I can change this or that. So mu naught times epsilon naught is 1 over c squared, right? So mu naught is nothing but 1 over c squared times 1 over epsilon naught. That way I get as much as close as possible to that. Okay, so that's equal to 1 over 4 pi epsilon naught, and there is 2 c's. Why do I have 2 c's? Oh, one of the c goes with mine with shape. Yeah, okay, so that's the same as 1 over r, and there are 2 c's, so this is d cube r prime, and one of the c's I'll keep it with d by dr. Usually time comes with a c in relativity, and j also comes with a c, so I'll keep the other one with this. Remember that c times rho and j are, c times rho is the 4th component of j. So rho will be j over c. Right? So that's why I put the c. Okay, so that's reasonable. More processing, yes. I'll break this at this point. Okay, there's one more thing we have to do. Yeah, can I start from here? This is an in-between step, but next time can I start? It's a space, it'll take only 10-15 minutes, but I think it's better to concentrate on that. That is a current conservation that is needed. And I need. So basically, these 2 expressions are written in rho, like charge density. This is written in j, right? but I can rewrite this in terms of charge density using my current conservation principle. And then everything is in current density, which is nice because current density is, think of an antenna, you move, change your current in a source, and there is a signal that changes. So that's the idea that electric and magnetic field will be completely controlled by the current or the change in current. The derivative of that will give everything. So this integral will be the important thing. This is always that 1 over r is simple. This is all that decides your radiation in this far field approximation. Yeah, so let me stop here. Yeah, I should have been a little faster and then I could finish this off. But we'll continue next time. Okay, thanks. Any general questions?
We